Okay, so what happens if we add the x squared and the negative 1 over y to this function? Well, that changes fx clearly by giving you a factor, or a term 2x. So that your df, your fx dx becomes this, same thing we had before, but you have a plus 2x. And your fy, similarly, derivative of negative 1 over y is 1 over y squared. So we get a plus 1 over y squared here. So what's that going to do? That's going to give us a plus 2x and a plus 1 over y squared. Now, if we do test my equals nx, well, if we do my, derivative of the 2x is 0. It disappears. And similarly, if we do the nx, the derivative of 1 over y squared with respect to x is 0, so it disappears. So we get exactly the same thing here. So these two functions, this function of x here and this function of y here, are invisible to this test. Okay? So, our integral of m dx then, well, we're going to have, in our m, we've got a plus 2x. In our n function, we've got a plus 1 over y squared. So when we integrate m with respect to x, we're going to have, well, antiderivative of 2x is x squared over 2. And antiderivative of 1 over y squared is negative 1 over y. Okay? And those are the only differences up to this point between what we had before and what we have now. Okay, so when we set these equal, our integral of m dx is going to have plus x squared, and our integral of n dy is going to have plus 1 over y, and it's minus 1 over y. Okay? So this tells us that we can only reconcile these if g of x is that x squared and f of y is that negative 1 over y. So now we can't say that f of x equals g of x equals c, or f of y equals g of x equals c. We have to say that f of y has to be negative 1 over y, and g of x has to be x squared. So that our function now is no longer this plus a constant. It's this plus x squared minus 1 over y. And that would be an arbitrary constant, right? So now our solution is this plus the x squared minus 1 over y equals constant. Okay? In other words, this is equal to the constant. So if we hadn't known this at the beginning, this whole process, starting from this equation, would have revealed it to us. Okay? And that's really the process, and it's just a matter of being able to do the integrals and understand how starting from here allows you to rediscover what this was. And of course, when you're given a problem, you're not going to be given this. Okay? You're going to just have this, go through the process, discover what this is, then to check, do your DF, and see if it doesn't give you this. Now, the other complication you can have is it's not always in this form. Like, I could have written this, how about dy dx equals what? Well, you just move this over to the right-hand side, right? And then divide this by the negative of this, and you'll have dy dx, right? Okay? So let's see, your dy dx would be, divide, you know, gotta be careful here, right? We're going to have this equal negative of this, right? So we're going to have to divide by this and multiply by this, so we're going to get, I think,
That one guy who showed up in one class, he said,
doing this in my head, it's always risky. Now, since I didn't have room, I didn't write the things that come off of the x squared and the 1 over y. But you see, and we'll check this in a minute, but you see that this doesn't look anything like this. Okay? So you might have to rearrange this to check to see whether this is exact or not. You have to rearrange it. You'd multiply both sides by the denominator, and you get this times dy. Multiply both sides by a dx, and you can't really do that, but I think, you know, it comes from the properties of differentials that you can get away with it. Okay? That you're going to get this times dx on the other side. So if you then subtract that from both sides, you're going to have the original equation. Does that make sense? Yeah, in other words, you got to do some algebra to rearrange the thing. And it could be even weirder than this. But it's just simple algebra to get it in a form something times dx plus something times dy and test it to see if it's exact. So you got an equation you don't know what to do with. No method that you can think of works. This is clearly not separable. Okay? Dy over all this equals dx over all this, you know, forget it. You're not going to separate it. Okay? It's just one of the things you always want to check, especially if it's really ugly. Okay? Because this is pretty ugly, right? If you're trying to use the methods that you have seen already with this, you just say, oh my gosh, start tearing your hair out, and pretty soon you take your bald self off and do something else, okay? But if you think, okay, well, let's test whether it's exact. It's easy to test. I mean, it might be a little tedious depending how ugly the terms are. This one wouldn't be bad. Those derivatives are pretty easy to do, right? Okay? So you get this. And you discover that it's exact. You say, oh, well, great. And then you just follow the process.